Good morning, everyone. How are we all doing today? Can you hear me all right? Good. Okay. Well, I'm so excited to welcome everybody to our 2023 series of the Saturday Physics for Everyone. This is an exciting year for us since it's actually our, sorry, does that help?
Just use this one.
Okay. We'll try again. Thanks. Try that again. All right. All right. This is our 30th year of the Saturday Physics for Everyone program, so we're very excited for that. We started back in November of 1993, so coming up on 30 years. And we've actually been working on digitizing some of our old tapes that we recorded back in those first early series, and so those will hopefully be available on our YouTube channel sometime this year. And we also have a couple of exciting commemorative events coming up this fall, so stay tuned for those for 30th anniversary. So for those of you joining for the first time, my name is Irene Lyra Ansager, and I'm the coordinator of undergraduate recruiting, research, and placement here in the physics department. So that means I get to work with students who are interested in becoming physics majors, as well as our students who are already here looking for research opportunities, and then what are they going to do after they graduate. And then for the series, so as I said, this is our 30th year, and the Saturday Physics for Everyone program is an opportunity for us to share our research with our community. So we're excited to be able to offer 6 lectures this series, and we'll start with Professor Lucas Wagner. And it also gives you an opportunity to see what your possibilities could be if you wanted to pursue a physics major in your future. So I'll give a quick introduction to our lecturer today. Professor Wagner received his bachelor's degree from North Carolina State University in 2002 and his PhD from the same institution in 2006. He then worked as a postdoc at Berkeley for 2 years, followed by a second postdoc at MIT in 2009. In 2011, he joined the physics department here at Illinois. He has pioneered the use of many-body electronic methods, in particular, quantum Monte Carlo methods, to treat interacting systems of electrons in materials. His group has used these techniques to clarify the physics of strongly correlated systems, such as the high-temperature superconducting cuprates and vanadium dioxide. His group has developed new techniques to derive the collective physics of interacting quantum particles from these detailed calculations using data-based techniques. Professor Wagner is also active in software development to enhance the availability of quantum many-body methods. He developed the QWalk package for quantum Monte Carlo, which scales these calculations to more than 1 million threads. Recently, he has been developing the PySCF, Python-based simulations of chemistry framework, and the Python-based quantum Monte Carlo ecosystem for many-body quantum projects. Finally, Professor Wagner is directing our new major, Computer Science plus Physics, which will have its first cohort of undergraduates in the fall of 2024. This new major will blend our CS plus our computer science and our physics degrees to give students the skills they need to understand and carry out quantitative models of physical systems, which is a major theme of the talk today. So with that, please join me in welcoming Professor Lucas Wagner.
Thank you very much. Thanks, Irene. And I should point out first that Irene has been so important also in the development of the CS plus physics degree. And we're really excited that that's coming online finally. And before I start, I also should say, please feel free to raise your hand, ask questions. particularly if you think it's a simple question or something that you don't, maybe you're scared to ask it, but don't be scared. I won't judge you. So anyway, it can be a little bit technical, so I would like to be able to explain things that are relevant for you. So I wanted to talk about computational physics, kind of in general. And so I first want to start talking about why computational physics is so kind of, in some ways, inherent in the study of physics. And to do that, I want to first start talking about why physics, I think among the many fields of study that we have, is so special. And okay, I know that it takes a certain type of person to look at this and say that's special, but a lot of people take physics and they sort of bounce off of the mathematics of it, of course, and I understand that. But that's also part of what makes it quite beautiful, because it's quantitative, right? So we have all these formula, and these are the type of formulas that you will often see in an undergraduate course in physics. And these things describe our world, right? So these are mathematical formulas. They're very precise. They describe our world to kind of ridiculous precision, sometimes to 15, 16 digits of precision. And they really seem to work. And so I think that's something quite special about physics, is that we have these really, really precise descriptions, right? And we do this in our classes. We say take F equals ma there, and we solve it, and we find how a closed form, mathematical, beautiful solution for how a ball moves through the air or something like that, right? We all kind of have done this before. We think that this is also applicable to much more complicated situations than what we study in our classes. But what happens is that very quickly, you stop being able to solve these equations. So even though we believe they describe our reality extremely accurately, we can't solve them using our pen and paper and our algebra very well. And it actually happens quite quickly. So this is for the famous three-body problem. I don't know if you've heard about this. That's different from the two-body problem of moving a couple to a new job. But the three-body problem, you have three bodies, and this is just the center of mass. And we don't have a closed form kind of algebraic solution for their motion, right? So for example, if I take three bodies, this is what it looks like when I have three gravitationally interacting bodies here. And you can see that they're going all over the place, right? This is actually what's called chaotic motion. But they move around and they go in this very complicated way. And we don't really have kind of an algebraic closed form solution for this. We can do it on a computer, though, fairly easily. Right? And the way we do it on a computer is really, really simple. We just have F equals ma. We calculate our forces. We propagate our positions forward a little bit, and then we calculate our forces again, and we just keep doing that iteratively. And so, I mean, this is a really nice quote that kind of sums this up. This is from Martin Rees, who's an astronomer in the UK. And he said, a physicist is like someone who's watching people playing chess, and after watching a few games, he may have worked out what the moves in the game are, right? Those equations are the moves in the game. But understanding the rules is not being a grandmaster at chess, is it? That's just the starting point. And even if we understand the laws, like actually understanding their consequences and actually using them to model the world around us is a whole nother effort. Okay. This effort's been going on for a long time. This is a really nice book. I kind of stole a story from this book from Thomas Levinson. It's called The Search for Vulcan. And it's really mostly focused in the 19th century. And so in the 1800s, we didn't have quantum mechanics. We didn't have general relativity. We had E&M. We had electricity and magnetism. We had Newton's laws. And interestingly, Newton thought that we needed some kind of godly intervention to keep the solar system running. He didn't think that it was purely mechanical. However, Laplace came along and actually showed that you didn't need that the solar system was actually completely stable. And then after that, people thought, and in fact, Laplace mentioned this idea that the universe is mechanistic. You have Newton's laws. Everything kind of goes like that. And so one project that was a major project in physics was to say, OK, how does the solar system behave based on these mechanistic laws? Can we actually predict the motion of the entire solar system due to these laws? And as you might note, that's a few more than 2 bodies. It's several bodies. It's like many more bodies. And so it's difficult to write down a closed solution. They didn't have computers then. But what they did have was they did have pencil and paper. And so they would just crank, right? They would just crank by hand these numerical solutions. And so Leverrier was the person who took up Laplace's mantle. And so we have the solar system here. This is the outer solar system. And at the time, this one here, Neptune, was not known. Right? We didn't know that that existed. That hadn't been, you can't see that with your naked eye. Actually, you can only see Jupiter and Saturn of these with your naked eye. Uranus was found just by happenstance. Somebody noticed a star was moving in a telescope, and that's not supposed to happen, right? And so they saw Uranus. But then, Leverrier spent years computing, okay, what should be the dynamics of the solar system, given that all the planets are pulling on each other, and you work all that out, and what you find is that Uranus was too slow, right? It went around too slowly. It takes a long time to go around, but it went around quite too slowly even for that. And the thought was, well, what could that be? One thought is, well, Newton was maybe wrong. He's like, no, that can't be true. And what he said instead was, okay, maybe there's another planet. And he actually worked out through computation where Neptune should be. And he told the observatory in France, where he was an important member, to go look for it. And they said, you know what, we have better things to do. And so he told someone in Germany, an observatory in Germany, to look for it. They actually looked for it. And they in fact found Neptune more or less where he thought it might be, because of the basis of computing what the orbit of Uranus should be, what Uranus should be, right? So that made him extremely famous, and that was viewed as a triumph, right, of this mechanistic view of the world. And the precision's important, right? I mean, because if you said, oh, well, I can only compute the orbit of Uranus to 10%, you don't see it, right? Because you need to say, oh, that's off by 3%, and I know it's off by 3%. You need that computation to be accurate enough to actually make these things. And so he said, okay, great. I'm the best in the world. I'm going to compute the movement of all of the planets in the solar system. And he did so. He spent years and years and years doing this calculation. And everything worked, except one thing that didn't work, which is the precession of Mercury. This is a famous thing in physics circles. And so precession, just to understand what precession is, so this is actually precession of a fake planet. None of our planets actually are this oblong. That would be a very hot day here and a very cold day here. So it doesn't look quite like this, but it lets you see what precession is. So what happens is that due to the influence of other planets and as we'll find out, general relativity, where the close approach is kind of rotates around as planets orbit the sun. And you can compute that, and he computed it out. Leverrier computed this out. And he found that it should be rotating 526.7 arc seconds, which is not that much, per 100 years. The actual observation is 565. And that doesn't seem like very much, right? But if you're very confident in your calculation, if you do your calculation very carefully, this is a problem. And he actually thought that this was due to another planet. That's The Search for Vulcan. This is a great book. Go read it if you can. But he actually thought this was due to another planet that was near the sun that we hadn't seen yet, and which they called Vulcan, because Vulcan, of course, is the god of the furnace, and that's why it was called Vulcan. And I think that might be where the Star Trek Vulcan came from. But he suggested that might be that, and of course, it's not there. And what it was ultimately resolved maybe about 75 years later by the development of general relativity. So that was basically, that was the way we knew that we needed new laws of physics, was by doing a good calculation on the currently known laws of physics. So that was a long time ago, and that was pre-computers. And so we can jump forward a little bit and talk about when we actually started to have digital computers, right? So it's fast computers. And very early on in the development, so this is 1946, Ulam realized he was, I think this quote is wonderful because this quote really tells us where ideas come from, right? They come from these kind of times of where we're not doing anything, where we're kind of stuck, right? So he said, my first thoughts and attempts I made to practice the Monte Carlo method, which is a type of method I'll talk about in a little bit, were such by a question that occurred to me in 1946, and I was convalescing from an illness and playing solitaire. So he had nothing else to do. He was just sick, and he was playing solitaire. And he said, you know what? I wanted to know, what's the chances that a Canfield solitaire, just a type of solitaire, laid out 52 cards would come out successfully, meaning that it would come out perfectly in the order that would be solved, and that you can solve it. And he said, after spending a lot of time trying to estimate it by pure combinatoric calculations, I said, you know what? Why don't I just try it 100 times and just see how often it happens? How often can I win this solitaire game? And that's actually kind of the idea of Monte Carlo, is that you say, okay, well, instead of trying to kind of do a combinatoric and be really clever about it, why not just try it a bunch of times and see how it goes? And sometimes that can be really helpful. And he says, okay, this was already possible to envisage for the beginning of the new era of fast computers. That's not fast now, but, but I immediately thought of problems of neutron diffusion and other questions of mathematical physics and generally how to change processes. And these were really used in the development of atomic energy and atomic things already at that point, right? This is Los Alamos. So that's kind of very early on. We just barely even had anything that can compute at all automatically. And immediately, physicists were thinking about how to do computations using them. OK, so since then, things have changed a lot. And two main things have changed a lot. One thing that's really changed is the availability of computation. So what this is the top 500 list. So this is the top 500 computers in the world that are publicly available, i.e. not being used by a three-letter agency. And so here, the green one is the sum of the top 500 computers. The triangle is the number one. And you can see that it's flat sometimes, because sometimes they take a crown and nobody overcomes that computer for a while. And the blue one here is number 500. And so this list actually only goes back to 1993. But if you look back, actually 1993, that's when this started. Yeah, it goes back to the start. Like most things started at 1993. OK. So if you look back, though, if you look at iPhone 13, which is already out of date, I suppose, but an iPhone 13 is here. So an iPhone 13 in 1996 would have been the fastest computer on the Earth, right? In 2003, which Irene nicely reminded me I was in grad school at this time, and also reminded me that was 20 years ago, that would have been on the top 500 list of computers, which to me doesn't feel that long ago, right? I was doing calculations at that time. So we've had this huge change in what we can actually compute. And you can see it's sort of leveling off, but this is a log plot, right? So yeah, that's actually something to keep in mind. This is a log plot. It seems to be sort of leveling off, but geez, it's still a lot of compute that we can do. Just to say, like, one flop per second, that's one floating point operation. So that's like one adding or multiplying two numbers, right? And you can do many, many, many of those per second. So that's one thing that's really changed. So what Ulam had was much, much worse than an iPhone 13. It was something that could do like tens of flops, tens of operations per second. The other thing that's changed is that physics itself has changed, right? So if you think back to Leverrier, he was using by hand calculations to do Newton's equation, F equals ma, right? That is physics 211. And we have a lot of classes after that one. And so those classes are really about going to more modern physics, right? So modern physics, we have this standard model. And the standard model is a whole collection of particles. It's described using quantum mechanics. And as far as we know, kind of up to kind of enormous energies and tiny length scales, as far as we know, this describes everything that we can observe. Right? Everything that we have ever observed, as far as we know, can be described using this plus a little bit of general relativity. And so you can kind of say this is sort of a root of physics that's known, right? That somehow we know that everything should come from that. And then if you kind of start going from these very small length scales, which is the standard model, and you start going up in length scale, then you get other things which I call, as a condensed matter theorist, particle physics stuff. It's a technical term. And then, on the other hand, you have, as a branch, you have electrons and nuclei, right? So you have kind of the chemistry type things that you've learned about in chemistry, where you have atoms that are made of electrons and nuclei. And pretty much everything that we interact with on a day-to-day basis, right, is really described very, very accurately using quantum mechanics of electrons and nuclei. So like the fact that we can see through the glass, the fact that the LEDs are making the light to project this image, unless that's a very old projector, the fact that superconductors exist, the fact that metals exist, the fact that people exist in principle are all coming down from this electrons and nuclei model. And as far as we know, this is extremely, extremely accurate model for that. So we kind of are now in a situation where for many things, we are sort of back to that mechanistic view, but instead of Newton's equations, we have quantum mechanics that's telling us how things behave, right? So some examples of things that are going on here. So for the particle physics stuff, so this is the muon G-2 that's going on at Fermilab. So this is a check to see, is there anything past that standard model, right? Is that standard model actually predictive? And so what they do is they have a muon. A muon is like an electron. It's part of the particle physics stuff. And electrons and muons both have inherent angular momentum, which means that they have inherent magnetic moment. And there's a constant of proportionality. That constant of proportionality is actually determined by all these terms in the standard model, right? So actually computing that constant of proportionality is a challenge. And measuring it is also a challenge. So this thing here, it sends these muons around, and it measures the angular momentum of the muons, and it measures their magnetic moment. Question? What do I mean by magnetic moment of a muon? So it's kind of like you imagine a magnet, right? So you imagine a bar magnet, and you shrink it down really, really small, and so it's kind of like one thing, but it still has that magnetic field. So the strength of that magnetic field would be the magnetic moment. What's creating the magnetic moment for the muon? The magnetic moment is created by muon as a charged particle, and a charged particle, when it spins, creates the magnetic moment. So if you have any spinning charge, that will create magnetism for you. And of course, that spinning actually involves interactions with basically all the other particles in the standard model, and those affect what magnetic moment you get, right? And so it's actually very similar if you go back to the solar system problem, right? That's how it actually spins and how that turns into a magnetic moment is dependent on interactions with everything else. And you want to compute all that everything else and see, do you actually get the right magnetic moment, right? So very similar to the orbits there. Except it's happening at like femtometer scale. It's really small. Any other questions? Well, okay. So that's that, and so these are calculations, and one of the leaders, and I should have put her image up here, Aida El-Khadra here at Loomis. She's been leading this effort of actually computing what the magnetic moment of the muon should be, and these are all the complicated like interactions and so on that they have to consider in their computations. And the experiment measured the relationship should be 2 plus something. This is the plus something. And the experiment measured 0.0011659259, and the uncertainty is 22 on the last two decimals, right? So they measured in the experiment to that degree of accuracy. And then with the computation, in 2020, they did a calculation here. And so if you look at it, they're looking at this magnetic moment deviation minus all of this bit here. So they're only looking at this like 5.9 bit basically, or actually just past it. And they have their measurement here, and then you have a calculation there, right? And so their calculation went there, and then now some revisions on the calculations have kind of brought them closer into agreement. And so the big question there is, again, whether or not the standard model, what we think describes everything, does it actually describe everything here? And they're looking at that degree of precision. And that's why we need this like strong computation, because otherwise we'd never be able to compute this to that accuracy here. And she uses these huge supercomputers and does coding and does all this fun stuff. And so, so that's one example in terms of the fundamentals of physics. Now, my research is actually in what's called condensed matter, or some people used to call it solid state, or some people used to call it squalid states, or some people used to call it the study of dirt. But it is the study of stuff that is kind of everyday, right? So all the things around us, kind of what we call like low energy physics. And this is the electrons and nuclei thing, right? So as far as we know, most of the things that are around us, that we observe, that we interact with kind of every day, are pretty well described by just a model of electrons and nuclei, and then quantum mechanics, right? And so these are some equations. You don't have to understand them in detail, but just to say, there's kind of an equation we want to solve for the motion of all these guys, right? But I do want to talk a little bit about the object that we need to solve for. And actually, because of this object, you'll often hear that people say this is impossible. And so the object we need to solve for is called a wave function. And the wave function tells you the probability of the particles being at any given location, right? But the thing is, for more than one electron, which we are made up of many more than one electron, if we want to model people, for example, then we have the position of each of the electrons. So it is actually a function of each single electron that you want to track, right? So instead of having, in Newtonian mechanics, you would be tracking the position of each electron altogether. In quantum mechanics, you actually are tracking a function of the position of all the electrons. And so if you do some counting, if I have 10 electrons, and I represent them on a 10 by 10 by 10 grid, right? So if I say, okay, this electron can be here, 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 10 by 10 by 10, that's 1,000 possible places, then the dimensionality of that function, which is what we call the Hilbert space, is 10 to the 30th, right? So that means that to represent that wave function, you need 10 to the 30th numbers, which is a lot. And so we find this, this is a known difficult problem. And we know that some of these cases we cannot solve for this wave function within a known computational resources. On the other hand, there are a number of cases where we know that we can solve for it. Even though it seems like it's infinitely large and exponentially large, we can still solve for it. And so there are some that we know that we can solve. And of course, the way that this always goes is that you have the ones that we know are difficult to solve for, and the ones we know we can solve. And then there's all the realistic ones that we actually care about, and they're neither of those two. So we don't know, we currently don't know, for something like, solving for the behavior of a piece of wood or solving for the behavior of a piece of glass, we don't know if that's something we can do efficiently on a computer or if that's something we cannot, right? We don't know that right now. But I think it's maybe useful to think a little bit about what it is we're trying to describe first. And so I want to show you some pictures of some wave functions. And this is actually the simplest possible interacting system I can come up with, which is hydrogen 2. So it's the simplest molecule that exists. It has 2 electrons. And what I did here is I have 2 protons and 2 electrons. And I took one of my electrons and I just fixed it there. And when I do that, I can then scan for the wave function of the other electron. And you can see this looks, hopefully from chemistry, you guys, this looks familiar. This looks like a bonding orbital from chemistry. Yeah? Can I get a shout out from my chemists in the audience? And it kind of looks like a bonding orbital, except for the fact that, that the value of the wave function is smaller here. So blue means that the value of the wave function is large, which means that it has a high probability of being there. And the white here means that it has a lower probability, right? So, so for this case, this electron here, one electron will tend to avoid the other electron. This hopefully makes some sense because electrons are both negatively charged and they will tend to avoid each other, right? And so this is what's called weak correlation because it actually, you can kind of coarse grain and you can kind of say, well, yeah, this electron's moving around and maybe it avoids this one a little bit, but just on a small scale, right? Maybe we can just kind of coarse grain it out. And we call this weak correlation. However, it's quite strong. So this is silicon. This is a chunk of silicon. And silicon is very important to our daily lives, as we all know. It's very important because it's a semiconductor, right? And so it has a band gap of 1.1 eV. That's slightly below visible photon energies. That's why it looks sort of black here. It's absorbing the photons. And that energy is quite important because it means we can modify its behavior by doping it. We can put other materials in it, and we can control whether or not it insulates or conducts, and that's how we make transistors, right? So it's very, very important that the gap to excitations here is 1.1 eV. If you don't put in those correlations and you do a calculation, you get 5 electron volts. That's a factor of 5 off. And you would say that silicon is transparent to visible light and basically like a piece of quartz or something like that. So you get completely wrong predictions if you don't include even these like what looks like very small sort of correlations of like one electron versus another. You have another question? What do I mean by band gap? So I mean by band gap, so in 214, which you're taking, we will talk about it in detail in about 3 weeks. But I'll give you a more simple explanation of it. So band gap here, what that means is it's basically the lowest energy type of light that it will absorb. That's basically what we mean by band gap. So for example, something like glass. So we know that the highest energy photon that we can see with our eyes is about 3.5 electron volts. So that already tells you that glass has a band gap which is larger than that because all of the light goes through it. A metal has a band gap of 0 because it's very easy for electrons to move around in it, right? So you can add and remove electrons from a metal very easily, and that's a band gap of 0. And so basically what we're doing when we have a semiconductor is very hand-wavy. I know that there are some semiconductor experts here in the audience, but very hand-wavy. We're sort of driving the band gap. We're controlling it in a certain way in our computers, right? So we're allowing it to conduct or not conduct electricity. So that's kind of why that's so important for actually understanding the materials and so on there. So there's weak correlation. There's also strong correlation. So in this case, what I've done here is I've taken my molecule and I've pulled it apart. And that puts it into what's called a strong correlation regime. And in that case, you see the wave function of my first electron is anti-correlated with the wave function of my or the position of my second electron. So when this electron is here, that means this other one can only be over here. It only has probability over the other proton, right? It kind of excludes it. And if this one happened to be over here, then the other one would also be over here, right? And that's what's called strong correlation. And strong correlation is very interesting to physics, in physics, because you can get really interesting behaviors out of a strong correlation. For example, magnets. So magnets actually work based on a correlation between electrons. So what happens is that the electrons repel each other. Remember I said that electrons have a magnetic moment, right? So if I have one electron by itself, then it has a magnetic moment. And that magnetic moment is the magnetic moment that we see in magnets, right? Now, if the electrons are kind of not correlating like that, then their magnetic moments will tend to cancel out. You'll get one that's magnetic moment pointing this way, the other one's pointing the other way, they'll cancel out. But if they repel each other, then you can actually get them lining up, and you can get a magnet. So that's how magnets work. Songs to the contrary, we actually understand how magnets work pretty well. But another case where strong correlation is very important is in superconductivity. So this is a superconductor. This is a veraticium, I don't know how to say his, Vsauce, sorry, thing. But he had some really cool cinematography on this. And this is a high temperature superconductor. By high temperature, we mean liquid nitrogen temperature, just to be clear. But he's taken the superconductor, he's cooled it down, and you can see, well, with the camera, with the infrared camera, you can see, of course, this is cold, and it's sitting on top of magnets. So we have strong correlation twice. We have the superconductor here on top, and we have the magnet on the bottom, and you can see the superconductor is floating. And this is something you can't really do with anything else. Like, nothing else will do this. It locks in place, and you can see it actually will go underneath the magnets. It's just kind of stuck to the magnets. It does these really cool things. And actually, we have a demo here where you can do this in person. It's not that difficult. And he has a pizza shirt. And he goes into the details of why. So basically what you're doing is you're locking in these supercurrents, these vortices of charge currents that are really supported by the electron correlations in the material. And when you put in the magnetic field, you actually lock these vortices in. And so it resists both pushing in further, because you would have to create more vortices, or pulling it away, because you would have to destroy the vortices, right? So it locks into the magnetic field there. This also has zero conductivity, right? So it doesn't resist, I mean zero resistivity, I should say. It doesn't resist any electrical current at all. And this is a case where people will often say we don't know how this works. That's somewhat true. We don't have a very good model for how these things actually superconduct. So it's not quite true that we don't know. We have kind of a vague sort of idea of how they work, but we don't have a good model of it. And we believe that we need to be able to treat this electron correlation better to be able to understand why these things behave. And so I just wanted to talk about a little bit, at least try to explain what I do. So what I do is I try to describe this correlation. I showed you correlation for 2 particles. That's pretty easy, we can do that. We want to be able to describe it for hundreds or thousands of particles, right? And so how do we do that? We use Monte Carlo. So we use the same methods that Ulam suggested. So the same methods of, instead of trying to figure out exactly how each the whole function, what we're instead going to do is we're going to throw dice, and where the dice land, if the dice land more in one place than another place, that's going to be where the wave function is large. If the dice land less in another place, then that's the wave function is small, right? And so for example, this is one instance. So this is graphene actually. But these are carbon nuclei. this is kind of the average electron density here in the gray. And the red is one deal, if you want to think about cards, of cards, or one instance of the electron positions. And we set up these mathematical systems in such a way that as we roll these dice, we actually get the right wave function. And so here's one example of how that works. So this is a one-dimensional system. This is a system we will solve in my class, Physics 214, in about a week and a half. So, so just a little preview for you guys. And so this is a particle moving in a quadratic potential. So basically, it's a particle in a spring, right? It's a particle in a spring here. And that's the potential energy curve there. And we set up with a guess for the wave function here. This is our first guess. And we throw our dice according to that guess. Now, that guess is the wrong answer, as you guys here in my 214 class will know in a couple weeks. But what we do is we take our dice and we throw them. And we threw them evenly. And then through this process, which we've set up, they have a birth and a death process. They wander around. And at the end of the process, you actually get the exact wave function. And this is in one dimension. So this is for one particle moving in one dimension, so you can see it. But we actually do it for 1,000 particles moving in 3,000 dimensions in our calculations. That is harder to visualize. But we can do it on the computer, right? So, so that's the basic idea there. So that's one method to do that. And it actually turns out that there are many different techniques that try to do this. And I'm not going to go into this in detail. There's many techniques. And they all have acronyms. And so if you're in this field, you get to learn we call it alphabet soup, right? Because we have many techniques, and they all have approximations, and they're all trying to describe this single problem. They're all trying to approach this single problem in different ways. And so we have this question, which is, how close can you get to exact solutions, right? Remember how important having accurate solutions is for understanding the physics, right? We talked about this before. How close can we get to exact solutions with these approximations that we have, right? And so this is a project that I led with the Simons Foundation. And it took this many people to answer this question for some pretty simple systems, right? So we got together. It was a big collaboration of people. And what we tried to do was we said, OK, how much do we actually believe the calculations that we have, right? What we can do in terms of understanding these many-body electron systems. What can we do? And so we did some test systems. And you don't have to worry too much about what the test systems are. We got up to about 30 electrons that we could really benchmark and get everybody on board. So it's not quite enough. But it's actually pretty non-trivial. We're solving for a function in 90 dimensions. So it's pretty bad. And actually, if you wanted to write down the wave function, we can discretize it a little bit and all that. If you do reasonable discretization, if you kind of put everything together, if you wanted to just write down the wave function, if you just wanted to say, how many numbers do I need to just write it down, you need about 10 to the 44 for the largest problem we considered. And that number for me is like, what does that mean, 10 to the 44? That's a big number, sure, but what does that mean? And so I kind of looked up like, what physically does that correspond to? And it's about the ratio in length between the observable universe and a proton, which is hard to think about. So one way of doing this calculation, if you were so inclined, you could take protons and line them up from one side of the universe to the other side of the universe. And the wave function is actually a complex number, so you need 2 dimensions. And so the wave function value could be represented by the x and y position of each of those protons that you've lined up across the entire universe. So that's maybe a good reason why people think this is impossible. However, it turns out that the wave functions that the approaches that we have can actually do a really good job approximating. And so what we managed to do was, and don't worry too much about like the details of this, but we kind of took all of our different word salad techniques and we compared them against each other, and this is the deviation. And what we found is that if you use techniques that we thought were good and we kind of compare them to each other, and they're coming at this problem from different directions, they're making different approximations, we can actually get to better than basically room temperature, right? So we can actually solve these problems accurately enough that the temperature sort of washes out the details beyond that, right? And so we can actually trust these techniques to pretty high accuracy. Even though this problem seems like it's just too big and too difficult to do, if you have good approximations, if you can kind of simplify the problem in the right way, we can actually make progress on this problem. And actually, our results are more accurate as far as we can tell than experiments for some things. I mean, obviously we trust experiment more than, than our calculation. Of course, experiment is the real world, but of course, experiment has uncertainties in it. And the uncertainties in the experiments are larger than the uncertainties in the theory now. But they do agree basically perfectly within their uncertainties. So the experimental uncertainties are there, and basically our uncertainties are sort of in this region here. So they basically line up directly. So we can directly compute from first principles, really from the basic physics, like this is basically chemistry, right? So that's one of the things that I do, which I find fun. Any questions about this one before? I'll just move on to some other things. I want to highlight some other things. No questions? Understood it perfectly. Yes? Yeah. What's the reference? So if you want to unpack this, so our reference is not from the experiments, right? So our goal with this was to have a reference which was experiment-free to see how well we actually solve the mathematical problem, right? So there's kind of two things. You solve the mathematical problem, and then you observe, right? And what you want to check to see is within uncertainties, are they the same? Are they the same within uncertainties, right? And so the statement really is saying that the uncertainties in our computed result are smaller than the uncertainties in the observed results. That's really what we're saying. But they're both kind of the same within their uncertainties, right? They agree with each other within uncertainties. Even for kind of a complex system, as I mentioned. Yes? Okay, what do I mean by 3,000 dimensions? Yes. Okay. So let's even go back to this situation here, right? So let's consider our protons as if they're fixed. Let's not worry about those guys for now. And let's just think about the electrons. So I have this wave function, which is a function of the position of particle 1 and particle 2. So that's already 6 dimensions because particle 1 can move in all 3 dimensions, and particle 2 can also move in all 3 dimensions. So I've shown you a 2-dimensional slice of a 6-dimensional function here. And as you add another particle, now it's 9, and then if you have 1,000 particles, it's 3,000. Yeah, yeah. Any other questions? Yeah. How much precision is needed for the calculation? Is that the question? Yeah. The question is how much precision is needed for a calculation? That depends on the question you're trying to ask, right? For something like magnetism, we can do that fairly trivially at this point, right? Not trivially, I should say, but with some effort, we can access magnetism fairly well. For something like superconductivity, which is actually much more subtle or much more gentle, we're starting to get to that, to being able to get to that precision. So it really just depends on what questions you're trying to ask. Something like the band gaps that I was talking about before, those are now considered, for the most part, fairly well understood, and they're less precision than, we need less precision to describe those. So it just depends on the problem, yeah. But just to kind of give you an idea of where we're at in terms of our calculational capabilities. Band gaps are not too bad. Magnetism is challenging but okay. Superconductivity is still kind of hard, yeah. and not clear we can completely do it. Yeah. Yes. Yes, that's a copper oxide molecule. Yes. Right. Okay, so the question is, why did we do copper oxide molecule? Well, the reason we did that particular molecule was that the high temperature superconductors that we're interested in eventually getting to are copper oxides. They have some of the similar chemistry, right? So that's a good starting point. What is dissociation energy? Dissociation energy is the energy it takes to take those two atoms and move them apart. The copper and the oxygen, yes. Yeah, just to pull it apart. And what was the last? What is year? Year is the year. It was just to track the experiments. Yeah, it's just to track the experiments over the time. It's just saying that the more recent experiments we're more likely to believe is kind of all we're saying. Yeah, the more years we get, the better we get. So yeah. We all get better as we get older, right? Yeah, so what happens is that as the uncertainties are getting a bit lower, if you look closely. The other reason we do it by year as well is that oftentimes the uncertainty, so this uncertainty is smaller than this. I think that's pretty clear. Yeah. So one thing that often happens as well is that I love my experimental colleagues, but sometimes the bars are too big, or too small, I should say. So sometimes they put these bars, but actually they should be bigger. So, but usually as the years go on, they get better, right? People just get better as time goes on. So, is the oldest? Yes. Oh, this is yeah. It's smaller than the dot. Yeah, yeah, yeah. Okay. Or maybe they didn't report it. I can't remember. I don't remember that particular point. Sometimes people just put a number out there and you just hope for the best, but yeah. Yeah. Okay, any other questions? Okay, cool. Okay, so other computational fields, I just want to shout out, since this is more about computational physics in general, we have things like biophysics, which is a really big group here. And they do some really amazing things where they're actually simulating entire cells and HIV capsids and so on in the computer using classical models. And astrophysics, this is a black hole accretion disk. So this is where stuff is falling into a black hole, which you're doing with calculations as well, where they do general relativity. So I just wanted to shout out those results. Those programs, because they're really cool. Okay, so I think I wanted to kind of go into a little bit of perspective, or at least some philosophizing about this. So you might ask yourself, and I think a lot of people when they come to computational physics, they say, oh, let's just simulate everything, right? Let's just do everything. And what that is something, of course, thought of by Laplace. Remember Laplace from the beginning of our talk. And he said, we regard the present state of the universe as the effect of its past and the cause of its future. And I think, at least from my perspective, this is also true with quantum mechanics. I don't think that's changed. Quantum mechanics is still a deterministic theory. It's just a deterministic theory of the wave function. So that's still okay. He didn't know about that. But an intellect which at a certain moment would know all forces that set nature in motion and all positions of all items which nature compose, if he's kind of verbose, but what he says that for such an intellect, nothing would be uncertain, and the future, just like the past, would be the present to it. Which he's trying to say that if you knew everything, then you could predict the future, right? If you kind of know what's going on right now, and you knew the laws of physics, then you could predict the future if you were smart enough, if you had enough computational effort. And this is called, he never called it this, but this is called Laplace's demon, which is kind of like the idea is there's this demon that knows everything and can predict everything in the future. Um, this, by the way, is the subject of a recent mini-series called Devs, in which they posit that a quantum computer could somehow do this. I don't think that's true, but it's a pretty good show, so I recommend it. So just to say, the answer is no. And you can kind of already see that we were struggling to even like do 30 particles, right? We have a lot more than 30 particles around. You can't really know what like the state of the entire world anyway. It's not really possible to do. And even computationally, we have limitations. So before you look on the left, look on the right. So when I was a young gamer, so this is what I had one of these things actually. And so this is a NVIDIA, this is a processor, right? This is a GPU, but it's the most powerful processors that we kind of have at a consumer level these days. And so this was 1999. And I just want you to look at something. This had a heatsink on it. And you look how big, it's about this big, right? And this recently came out, this thing. And I tried to scale them to be about the same size, about the same scale. But this is supposed to be about the same size as this, as you can kind of see it. And you can see that not only does it have 3 fans, but everything behind this, the chip on this thing is still like this big, right? And so the reason this thing is ginormous is that it's all heatsink. It's just this massive heatsink attached to a chip, a tiny chip. And so it's much more powerful. Like it can render, it's like insanely more powerful. We saw those graphs before. Actually, all the top computers are using a server version of this, which doesn't have the RGB lighting. But you can kind of estimate from thermodynamics, you can make a connection between information and entropy. And you can say, well, erasing 1 bit, so if you're doing computation and you're erasing 1 bit, that costs at least 2.9 times 10 to the minus 21 joules, right? So, okay, 1 joule is taking 1 kilogram and lifting it like a tenth of a meter or something like that. So it's not that much energy. And current processors are about 1 billion times worse than this. But you can see that we're kind of very much limited by heat dissipation. In fact, you can get better performance on your computer by cooling it better. So if you put better cooling on it, it actually automatically throttles. All of our processors are actually throttling like crazy all the time. They could go faster, but they're too hot. And that's why this high performance GPU has this huge heatsink on it there. So we're sort of limited by just thermodynamics and making a lot of heat. So we have a long ways to go. We could do better. But we are sort of limited. And if you kind of work the numbers in terms of what we would have to be able to do computationally to actually simulate everything, it's just the magnitudes don't line up. It just doesn't line up. So computation has to be used judiciously. You have to use it to answer the right questions and do computation on the right things. You don't get to turn off your brain when you're doing computation, which is what I tell all my grad students often. But for the future, I think the future is a lot about kind of being somewhat clever, trying to think about how to use computation in the best way. I tried to rewrite my talk with ChatGPT on the left. That's AI. It's being used a lot in computational physics these days. It does look like it could be really a way forward in kind of making some of these calculations better, making better approximations to maybe the many-body wave functions, for example. And other approaches as well. So that looks really promising. Less developed, I would say, on the right-hand side, that's a quantum computer. Right now, they are not in the case of actually replacing classical computers for most computational physics purposes. But they're very interesting, and they're, of course, a very valid method of research, right? But I think what's really changing things right now is the AI stuff. It actually gave a pretty good answer, as usual. But yeah, that's basically a Wikipedia page, though. So I don't know if that's really fair. OK. And I talked about, I think this is all very important, and this is one reason why we started the CS plus physics degree. And I think it's worth kind of noting that computational physics has really affected many other fields. And there's a back and forth, of course, right? We give things out and we steal things and all this stuff. So material science. So most semiconductor companies have a materials design wing, right? They actually do simulations similar to what I was talking about with electrons and so on to help design new materials for semiconductors and understand how those work, other functional materials as well. Biology, they do drug design using calculations. They actually will simulate entire viruses and try to understand how they work. Finance, a pretty good fraction of my graduate students have been snapped up by finance companies because modeling financial systems is very similar to modeling physical systems. And so they use them for that, and they make a lot more money than me, and I'm happy for them. But, but they do well. I'm really proud of them. And data analysis, autonomous vehicle design, you need to model the physical world. You need to do a computation like, is that car going to hit us or is it not? That sort of thing. New battery materials is so important now. Energy storage problem is really important. Chemistry, a lot of simulations being done in terms of trying to find new battery materials. Recently, Toyota came out with an announcement, who knows if it will work out, but of a new only solid state battery, which could possibly result in cars that can go 700 miles on a single charge. We'll see if it actually happens. That was an announcement, not a product, but I hope it works out. And I mentioned quantum computing, AI. There's really a back and forth. Of course, quantum computing is computational physics to a large extent. It's just moving to the next level. And AI, of course, has taken a lot of inspiration from the techniques that I talked about in computational physics, and we've taken things back, and it's not even clear that they're different. It's a gray area going all the way through, but it's a place where this has some impact. Yeah, and so I think it's an exciting field still, and it's an old field, as I mentioned. It's been around for a long time, but I think it's becoming even more important in our daily world. So that's what I had to say today. And thank you all for coming, and thanks for your attention. Happy to take questions if you have any. Yes? I'm sorry? Yeah. Mm-hmm. Yeah. Yeah. Right. Okay, so the question was, for many things, it's better to have a human in the loop in some sense, right? You want to have a human as part of it, especially, autonomous. People were promising in autonomous vehicles, you could just fall asleep, and that seems to not be a good idea. Seems people do it, but it's not a good idea. I think, for me at least, when I think about computational physics, computational sort of approaches, I don't think of it as being like a replacement of a human being involved. I view it as an augmentation, right? And so almost all of these things are better if you have a really, talented and aware human as part of this thing, right? So a lot of times it's not really about taking a human and taking people out, but it's about taking people and saying, okay, well, you use your brain for the things that you're good at, and then the computer will help you to do other things. That's typically how it's used, more so than, oh, you don't get to turn off your brain, and the computer doesn't do your thinking for you, I guess is one way to say it. Yeah. Yeah. And in fact, sometimes you have to do more thinking because you don't get, like if you're just computing the orbits of the planets all day, you don't have to, like you can just compute all day. But if the computer's doing for you, now you have to think about what calculations should I do, and that sort of thing, right? Does that make sense? Mm-hmm. Exactly. Like, I mean, just to repeat for the thing, but exactly what you said. I mean, if you want to be thinking about, is this a reasonable result? Is it something surprising that could be a discovery? Is it something that you might typically expect? These are all things that we really need humans. They're really important to have humans in there. Yes. Well, I think the question was in the material science design, like say if you're going to make a new semiconductor or just modify the existing ones, is the experimental part more important or is the computational part more important, or do they interact? And the answer is that it's a collaborative experience, right? So usually the way that it works is that a computational model, because you do typically quite idealized models, right? I mean, we're kind of limited in terms of what we can compute, but we know exactly what we're computing, so that has a good value, right? So you can kind of understand trends, you can generate ideas, but ultimately you always have to check it experimentally because there's always something that happens that you weren't expecting, right? And you have these things that are really hard to predict. Like for example, this is a little bit outside my particular area of expertise, but for example, what I understand is that some semiconductors are very resilient to defects being in them, right? You can make them and they can be defective and they'll just work great. And some, if you have just a few defects in them, they just completely fall apart. And it's very difficult to anticipate that, although oftentimes computationally you can go back and understand why that happened, but it's very difficult to anticipate it in some sense. So it's a really nice back and forth. And the other thing that happens, of course, experimentally, a lot of times you'll do an experiment and you don't really see atomically what's going on. So it's hard to understand what's actually happening, but then you can go and do a computational model and you can kind of match them up and understand what's happening at the atomic scale more clearly, which means you can then, say, modify it chemically or do something in your process to control its behavior. So it's really a back and forth. It's not like one is completely dominant over the other, I would say. Yes? I have to say, so the question was, I've made it very clear that it's been important for the past couple years, and I tried to make the argument that it's been important for the past couple hundred years, right? Which you say, and you say, okay, why has it been so long? Why has it taken so long to do a CS plus physics? And I would say thank you very much because, I mean, if you have an idea and somebody says, well, you should have done this a long time ago, that means it probably was a good idea, right? So, okay. I don't know. I mean, we've had for a long time, for me, I actually didn't do, I've taken one computer science class in my life. Just to say. I've written millions of lines of code, but one CS class. I was actually a math double major. And so what has happened historically is that people, and like another computational physicist here, Brian Clark, was a CS double major, right? And so people have typically been double majors, right? Or something like that, right? And so he said, that's how people have typically done it, or done minors and that sort of thing. And so he said, okay, well, we have enough people in physics who are interested in doing this now. Maybe we should do something that's more official, right? But I mean, when things happen, it's a combination of opportunity and will and all these things. So it's always hard to predict when things happen. Yes.
You mentioned in the class that if you know the current state of a system, you can predict the
Yeah, so the question was, is it true that if we know the current state, can we predict the future state, right? So that's what the equations of physics tell us, right? That's what they're doing. The question is, can you solve it? Can you actually do it? Can you, implement those equations, those mathematics? So that's one question. And the other question is, do you actually know the current state, right? And so typically, actually, in our modeling, like we talk about modeling the semiconductors from that previous question, a lot of times the difficulty is that we don't know what's actually in what the actual experimentalists have, right? So a lot of times the difficulty is knowing, not so much even like, I mean, okay, the computational part is hard, but knowing the current state is actually really, really difficult as well sometimes. So you need to know both those things. You need to have both those things happen. And yeah. And then that's what physics tells us. And then when we can try it and when we can do it, it seems to work. So that's pretty cool. That's what I loved about physics when I was first going into physics. That's what I really loved about it. Like you could sit down and like write some symbols on a piece of paper and like crank, 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 crank. And then it'd be like, exactly, this should be 1.73. And then you go and do it, and it'll be 1.73. And I think that's just, I don't know, for me, that's just so beautiful. And so that's why I did physics in the beginning. So yeah. What does that mean for free will? I have no idea. Okay. That's another question. Yes. So the question was, are there more computational, like in like physics, is there more computational versus theoretical? It's not really like it's kind of, there's a range, right? So somebody like me, I'm pretty far on the computational side. I work on algorithms. I do like actually big computations. But you go, anybody under the age of some number, generally speaking, does some sort of computation to augment, right? So even if it's even just Mathematica, right, that's using some computational algebra to help them do some of their work. That's like the least computational side. And then it goes all the way down to somebody like me who's running on supercomputers and all that stuff. So there's just a spectrum of people. And one year to the next, you might do more computation for the projects that you have. You might be doing more pen and paper. So yeah, it can vary. So is there a trend? The question is there a trend? I think it's just becoming more and more integrated as a tool, right? That's the thing. I think what happens a lot of times as tools come up is the tools become, at first the tools are sort of just for specialists, right? And so you have a computational physicist, and they're the only ones that use computation. And that's quickly becoming not the case in the sense that, I mean, that's been happening for years and years, right? That it's just been integrated as a tool into people's arsenals of tools that they can use. It's a little bit like asking, like, are derivatives, do you have calculus people or not at some point, right? Everybody does calculus. Everybody uses calculus in physics. Some people use it a little more than others, but it's always a tool that we have available to us. So computation is really becoming a tool that just everybody uses at some point, and to varying amounts depending on what they're doing. Yeah. But then we have the experts, and the experts are the ones who like push forward what we can actually compute and what we can do, right? So like a computational physicist these days is not just someone who does computation, but at least for me, it's like somebody who's pushing forward what we can do computationally. If that makes sense, yeah. Yeah. Yes.
Yeah, so thinking about computational physics in terms of the efforts to improve meteorology.
Uh-huh. Yeah, I should have put that. Actually, that's another one. Yeah.
The question is, do we really see any improvement in forecasting that we see in these other areas? And if there's this difference in improvement, what's going on that you're not achieving this improvement in the meteorological question?
Yeah. So the question was about climate prediction and meteorology. And the question was, one question is, are we seeing any improvement in our modeling? And the second one is, if we're not, then why? And this is way out of my field. So I can give my best guess. I can go ask my friends later in computational modeling and see how right I was. But my understanding is actually that the modeling has improved quite a bit. Now, there are certain limitations, right? For weather, there's weather and climate. Those are different things. So like weather prediction, you are pretty limited because it's a chaotic system. And so talking about knowing the conditions is very important, right? So for a chaotic system, you have to know the conditions really, really well to then predict what's going to happen, right? Because a slightly different initial condition will result in a very different ending condition. And so for weather prediction, from what I've been told, the knowing what our current conditions are is kind of the limiting factor, not the computational part of it, right? Just like the sensing. And you have to know that to that detail. That's my understanding for those guys. And so that's why you're kind of limited to a few days for weather. And then for climate, I believe the climate models have been improving, actually. They've been getting better and better. So, you know, it's slow, it's difficult, but you know, that's research for you. So, yeah. Yeah. Yes? What would be a good start in computational physics? Physics? Physics, so it depends on where you are exactly. But yeah, physics is really important. And it's interesting, like different people take to different things more easily in this field. And it's totally okay if you're good in, you know, different people have different skill sets, right? And you have different things that you're attracted to. So you should definitely follow what you're interested in first. I think that's the most important thing. Like whatever you care about, like what do you like to do? And it depends a lot on where you are. Like, so we have in our department, we have computational physics course. We have 2 courses, one at 200 level, one at 400 level, that are specifically doing computational stuff, right? Actually, we have 3 courses, now that I think about it. I forgot the one that I taught, actually. But yeah, I teach one as well for atomic scale simulations. And so we have 3 courses that are really like focused on computational things. So that's something you can do. And at the 200 level, it's quite attainable. You can try it out, see what you like. I would say that some amounts of computer science helps a lot. But not all of computer science for computational physics is necessary. Although to be honest, I've never regretted learning something, you know, about it. It's always been helpful. The other thing, I mean, applied mathematics is very useful as well. So any sort of applied mathematics, linear algebra, calculus, any of these things is so important for it. So those are kind of the 3 pillars of computational physics. We have CS, well, mainly physics, right? It's the subject. And then math and CS. And it's kind of like those 3 subjects are really the ones that support it. So anything you can get in those subjects, I think will help. Yeah. Okay. Oh, sorry. Yeah. Hmm. Mm-hmm. Mm-hmm. Okay, so the question was about, so I mentioned that you were paying attention because that was like, Irene actually mentioned this. Yeah, that actually I moved over to my shop to Python a few years back. And so we were doing C++ before that, which felt modern when I was in grad school. And before that, Fortran was the most common thing. And some people were still do Fortran. For some things, it's okay. It actually can be okay. So I'm fairly language agnostic myself. Once you've learned a few languages, it's not too hard to learn another one. So for me, personally, I'm like I like to keep kind of some consistency in my group and so on, just because otherwise we can't talk to each other. But so Python has done really well for us, and integration of AI and computational physics, it's already happening, and that's why, it's happening everywhere, and sometimes really well, and sometimes, but actually a lot of really good stuff, and so that's actually part of the reason why I switched over to Python, because everything was implemented in there, and I could use all these tools and packages without having to think too much about why reinvent the wheel. So so that I'm happy with, and I tend to try to move with the field. Like if the field's going to move somewhere else, then I'll try to move with it so that I can integrate with other people, other things. So I'm happy to move forward. Every move forward in some sense, in that sense, seems to have been better and made it easier as we learn better how to organize code and how to organize logic. It seems like it's just people are getting better and better at it. So I think that's great, and so it helps a lot. So when we went from the C++ code to the Python code, we went from about 60,000 lines, which took me. So I wrote those originally when I was in grad school, and I think I wrote actually like 500,000 lines. And then that ended up being like 60,000, because you keep rewriting things. And the Python implementation is about 5,000. So it went down by like a factor of 10 because of better coding standards and so on. And so I'm hoping if I move to something else, I'm hoping it'll be 500. And that's something you can see on one screen just about. That's really good, yeah. And then we can think more about physics instead of thinking about like how to add this number to that number in the fastest way possible, which is fun, but we have other things to worry about. Yeah, yeah. Yes. Sure. So about the computational ones, so the computational classes, 246 is the computational class. 214 is my quantum class for undergrads. And then there's 446, and these are taught by Brian Clark, who I mentioned before. He does a really good job with them. And there's also 466, which is the class I teach every other year. We share it with material science. It's about atomic scale simulations. Yeah. So the question is, does that, as far as earning certifications, I'm looking at Irene because she may know more about this than I do, but I think it can definitely count as part of the computational physics concentration. Is that right? And it can be just an elective, right? You can just do it, no problem. And they're required for CS+ physics when people come in later. Is there anything else you want to add? Is that the? So you can get a computational concentration, which I don't know if does it show up on your degree or?
So on the degree, it lists Bachelor of Science in Physics, but then like you could add details in your resume.
Okay, you would add it in your resume, yeah. Yeah, but so there you go. Good. All right, you're trying to kick me out. Oh, thank you so much. Yeah.